Hello, everyone. Thank you for joining me today as we begin our conversation on Chapter 6, which is with regards to the electronic structure of atoms. Specifically, what's going on with the electrons in an atom. Those electrons are pretty important because they are the ones that make connections between atoms to form bonds. And so to further elucidate how atoms make connections to each other, we need to visit in more detail what goes on with electrons in an atom. And so normally when I present this lecture in the summertime, it's usually actually around the 4th of July, which is convenient because I love to show this pretty picture of fireworks. I know it's not the 4th of July right now, but I showed this picture and these beautiful colors that are produced with fireworks because the colors that we see with fireworks are a function of the property of the electronic structure of atoms. In general, to understand the electronic structure of atoms, we need to understand and be able to do mathematics with concepts that we use with the concept of light. And so we're going to use this little vignette to talk about properties of light because many of those properties are shared with electrons. So when we talk about light, we can think about light in terms of three things: in terms of its energy, which we'll talk about more in subsequent videos, but also in terms, we can describe light in terms of these concepts of a wavelength and amplitude, specifically frequency. So wavelength, which is measured in meters, if you were to do a graph of a light wave, the distance between two peaks would be the wavelength. Okay, it's the distance between two consecutive peaks or troughs, actually. Amplitude or frequency is the height of that wave. And it turns out that color is related to the wavelength of light. So all of those fireworks that we saw in the previous picture, they all have different colors, so they all have different wavelengths of light. The intensity or the energy is a function of the amplitude or the height of that wavelength. We're going to talk a bit more about amplitude and energy with regards to electrons, and we're going to use this term called nodes that will be later on in the chapter. Right now, just know that for a light wave that can be characterized by frequency and wavelength, that if you have zero amplitude or zero height of that wave, that is called a node. So for example, in this first wave, I have 1, 2, 3, 4 nodes. So those are some terms that we use to talk about light. You may be familiar to you from a physical science class. We're also going to use these terms, specifically right now, wavelength, frequency, to speak about the electronic structure of atoms. Wavelength and frequency can be calculated and are related to each other through the speed of light. That is a constant called c. They are related to each other through these two equations, which is the second equation is really just the first one rearranged, where we have frequency, which is mu, is equal to the speed of light, c, divided by wavelength. And so you'll see two facts from that relationship, that they are inversely proportional. If you have a long wavelength, you have low frequency, but if you have a short wavelength, you have high frequency. So that inversely proportional relationship is going to be important to us when we do calculations shortly. Before we do some calculations, a note about the speed of light, the constant c. So on MindTab, usually I just use 3.00 times 10 to the 8. MindTab likes to take it out, and other texts like to take that constant out to one more digit. So you guys will have to yell at me in lecture and throughout the PowerPoint presentations, hopefully not too much, but I've gone back and I have changed all of my slides. So when we do calculations using the speed of light, we're going to use 2.988 times 10 to the 8. While you do need to memorize this relationship, this equation between frequency and wavelength, I will give you that constant for the speed of light. So let's go ahead and let's do some sample calculations. So let's say I have a yellow light and I know that the wavelength of that light is 589 nm or nanometers. And I want to know what the frequency, the mu, is of that radiation. So I'm looking for this little v, which is mu. To solve for that, I need to first take my wavelength, which is represented by lambda, and get it into meters. Because remember, the speed of light, c, is in meters per second. So once I do my conversion from nanometers to meters using that Greek prefix nano, that gives me 5.89 times 10 to the negative 7 meters. I can now take that, put that in the denominator with the speed of light in the numerator, and get my little pen here, and doing the appropriate division, I get a frequency that's in per second, which is great because that is the unit for frequency. So my frequency for this wavelength of light is 5.09 times 10 to the 14th. Many times frequency is also represented or expressed in hertz. 1 hertz is equal to second to the minus 1, so that will be the exact same number. So make sure that you know that. Aside from knowing the relationship between frequency and wavelength, make sure you know that relationship between seconds or cycles per second and hertz. Last slide for this little vignette about light and frequency and wavelength. This is just a cartoon to show the relationship again between frequency and wavelength. And you see that as the wavelength, so wavelength is on the bottom, frequency is on the top. As your wavelength gets shorter, your frequency increases and vice versa. And so what's plotted here, aside from showing that inverse relationship, is the areas of the electromagnetic spectrum, the areas where particular light energy falls on this continuum. Now, you do not need to memorize the specific ranges and frequencies for each type of electromagnetic energy except for the visible, because we'll be dealing with that most frequently. You should know that light that has a wavelength between 350 and 800 nanometers is in the visible spectrum, so you should know that. And you should also know just the relative strengths of these types of electromagnetic radiation. So you should know that gamma rays have a higher frequency than X-rays, which have a higher frequency than the far UV. So you should know the general trend for their frequencies and wavelengths. And how is so? How is that related to energy, the energy of a light wave? And how are we going to relate that to electrons? We will start to do that in the next video, which is going to introduce this revolutionary experiment that got a few folks the Nobel Prize called the photoelectric effect.